set? Good. So I hope everyone enjoyed PSET 1. So on the lectures section of the website, there is this bullet that says everyone may have to scribe 1 to 2 lectures depending on class size. So it seems like the class is small enough that I might have to ask people to scribe twice in the semester. Okay. In particular, there's no scribe for today. Oh, you're scribing? Oh, great. Okay. Oh, did you send an email or? Oh. Okay, great. Okay. Okay, great. Okay. Okay. And also, we do need 2 more people to sign up, help grade PSET 1. Everyone's supposed to help grade 1 PSET, so please sign up for that. I think we have 2 people, but there are 5 problems, so the TF plus 4 people would be ideal. Right. And PSET 2 is going to come out tonight, which has only 3 problems. So, and it will be due 2 weeks from yesterday. Okay. Great. So now let's get back to business. Last time we met on Thursday, we discussed a new problem. It was related to trend detection in streams. There were 2 problems. One was point query, specifically L1 point query, where there's an X, a vector X that's high dimensional, n-dimensional. It's being updated in a turnstile stream. And at various points, someone can perform a query. And the query takes as input an index I, which is between 1 and n, and you should output xi plus or minus some error term. Okay? Sure. Okay, great. And it's L1 point query because that's L1. You could ask for other norms. How's the volume now? Great. Okay. And L1 heavy hitters is you need to return a subset of 1 to n such that all the people who are epsilon heavy hitters, meaning they're at least an epsilon fraction of the total mass, should be in that list. And if you're not close to being an epsilon heavy hitter, then you're less than an epsilon over 2 heavy hitter, you should not be in the list, right? So this already implies, for example, that the size of L can be at most 2 over epsilon. How many people can have epsilon over 2 fraction of the mass? At most 2 over epsilon people can, right? Okay. And I was about to tell you how to solve this problem in the streaming model. We had a definition for epsilon incoherent matrices. So pi has columns, pi 1 up to pi n, and it's an m-dimensional, it has m rows. And it's epsilon incoherent, yeah? Here? Right, so think of it as a data structural problem. The data structure has to maintain x. And then there's one kind of query that's allowed, namely you query an index between 1 and n. Okay, and the answer, an acceptable answer to that query is the ith entry of x plus or minus an error term. And the promise should be that the error term is at most, an additive error term is at most epsilon times the L1 norm of x. It's an index, yeah, I think of it as like an index into x. Like I give you I, you should give me xi. Yeah, but I'm allowing error. Yeah. No, these are 2 different problems. Yeah, sorry. Yeah, we'll see a relationship between these problems soon, but these are 2 different problems. Okay, so good. So actually, to solve both of these problems, one thing we can do is use what's called an epsilon incoherent matrix. The columns of pi have unit norm, Euclidean norm, and the dot products between different columns are at most epsilon. So these are almost orthogonal vectors that are the columns of pi. And the claim is that you can use this pi, if you have an epsilon incoherent pi, you can use it as a sketch for actually both of these problems. Okay, so we'll see that now. And we talked a little bit about how to get pi from codes, okay? And you had a piece of problem about it. Okay, so proof of that claim is actually very simple. It's almost a one-liner. So our sketch is going to be is y, which is pi x. Okay, and we'll estimate xi as yi, which is ei transpose pi x, right? Oh, sorry. We'll estimate xi as pi transpose. Let me write that over. So the point is, since pi has almost orthogonal columns, pi transpose pi is almost the identity. That's the thing to keep in mind. So y is pi x. So x is roughly pi transpose y, which is pi transpose pi x. So we'll estimate xi as pi transpose y, and then the ith entry of that, which is equal to pi transpose pi x. Okay. And why does that work? Notice that pi transpose pi x, I, the ith entry of that, is ei transpose pi x, right? Which is equal to the dot product of pi ei, which, by the way, is just the ith column of pi. And something to keep in mind, linear algebra fact. The definition of matrix vector multiplication is that pi x is the same thing as the sum over all j of pi j xj. Okay, that's what matrix vector multiplication means. And then now we distribute this dot product. So there's the case when j equals I, and then there's the case when j doesn't equal I. When j equals I, you have pi I dot pi I, which is 1. So you have xi. And then you have the case where j does not equal I, xj times the dot product of pi I dot pi j. Okay? But these are at most epsilon in magnitude. So this is at most xi plus, this is equal to xi plus something, which is at most the sum of j not equal to I of the absolute value of xj times epsilon. Right? So in fact, the error is even slightly better than the L1 norm. It's the L1 norm not including I. Okay? And one way to write this, by the way, is I'm going to write something, and we'll see more of it soon, and in other parts of the course as well. So given pi x, we are recovering some x tilde, which happens to be pi transpose pi x, such that if you look at the infinity norm between x and x tilde, that's at most epsilon times the L1 norm of x. Okay? So this is what's called, and we'll talk about compressed sensing later in the course. This is what's called an L1 L infinity guarantee. Okay, and there are other guarantees you could shoot for. We'll put some other norm here and some other norm there, and you could ask, which kinds of guarantees are the strongest, and how big does your sketch have to be to achieve these different kinds of error guarantees? Okay, so that's something we're going to talk about more later. Yeah. EI is the ith standard basis vector. Yeah. So yeah, if you have a vector z, the ith entry of the vector z is just EI transpose z. Yeah. Okay, any other questions? Okay, so now the question is, what kinds of incoherent matrices can you get? So construction 1, okay, so the best construction come from codes. Okay, so there are other ways to construct them, but for now I'll just mention the codes because that's the best thing. That's the best thing we have. So using codes, I called them last time. What was my made-up notation? As long as you have an epsilon, t, q, n code. Just to recap, what does this mean? It means, what is a code? A code is just a collection of vectors. Each vector has length t. Each entry in that vector is a symbol between 1 and q. And there are n vectors. Those are the code words. Okay? And the epsilon means that if you look at any two different vectors, two different code words, they agree in at most an epsilon fraction of coordinates. And we saw last time that if you had such a code, then you get an incoherent matrix that has q times t rows and is epsilon incoherent. So now the question is, what kinds of codes can you get? One thing you can do is you can choose q to be something like 2 over epsilon and t to be something like, let's say, log n over epsilon. And I claim that random such code works with high probability. Okay, if you just pick n random vectors where each vector has t entries that are each entry is just independently a uniform number between 1 and q, I claim that it has this property. And why is that? It's basically just the turnoff bound. Okay, so look at any, fix 2 of the code words. We call them C and D. Okay. The expected number, right? The expected number of places where those code words agree is epsilon is actually t over q, right? Expected number indices where C and D agree is equal to t over q. You can write this as a sum of independent indicator random variables, t of them. Okay, so the expectation is t over q, and since this is a sum of independent indicator random variables, you can apply the turnoff bound, and you can say that actually not only is it t over q, but it's at most 2t over q with probability exponentially small in t. One minus that. With probability at least 1 minus exponentially small in t, you actually get at most 2t over q. That's the turnoff, that follows from the turnoff bound. So now if you set t to be something like, if you make this t big enough, right? Like some, not t. Actually, you're going to get something like epsilon t in this case. So t over q, basically. Yeah, sorry. Right. So the probability that you're bigger than the expectation by a constant factor is like e to the minus expectation times some constant. So as long as you make t over q a big enough constant times log n, which it is in this case, okay, then this thing is going to be, this thing here is going to be much less than 1 over n cubed. So with probability at least 1 minus 1 over n cubed, you succeed on these 2 code words. Okay? But how many pairs of code words are there? There are n choose 2. They're like n squared pairs. So by union bound over all the pairs, you can say that simultaneously, none of them agree on at most 2t over q coordinates. And 2t over q is exactly an epsilon fraction of coordinates. Yeah. Yeah, exactly. Yeah. So e to the minus log n, right? There's a constant here. So you can make this constant bigger by making this constant bigger. Yeah. Yeah, but 2 over q is equal to epsilon. So the number of indices where c and d agree will be at most 2t over q, which is exactly epsilon over q, which is exactly epsilon t. Yeah, so this is equal to epsilon t, an epsilon fraction of the indices, right? So questions? Don't be afraid. There are only a few of us. Okay, great. So now union bound. Okay. Union bound over the n squared pairs. Okay, great. So that implies m is O of 1 over epsilon squared times log n. Yeah? And then the second thing you can do is use what's called Reed-Solomon codes. Which is exactly your p-set problem using polynomials. Those are called Reed-Solomon codes. And if you solve that problem the way that we wanted you to solve the problem, you would have gotten that q is equal to t is equal to theta of 1 over epsilon times log n over log n plus log 1 over epsilon. Which implies that m is equal to theta of 1 over epsilon squared times log n over log n plus log 1 over epsilon squared. Okay. So if you think of epsilon as being a constant, like 0.1, this is log n. This is roughly log squared n over log n squared. So that's better when epsilon is not too small. But once epsilon is small enough, for example, if epsilon is like 1 over n to the 0.1, or 1 over n to the c for any constant c, that's 1 over epsilon squared log n. But log n divided by log 1 over epsilon is a constant. So this part just doesn't even matter anymore. So this is better by a factor of log n. And in fact, this thing is better than the first option when epsilon is like much less than 2 to the minus some constant square root log n. That's the transition point. Okay. Very great. And it's by the way, codes that achieve this kind of trade-off are called, codes that meet the Gilbert-Varshimov bound. If you read coding theory literature, this is the GV bound, and this is Reed-Solomon codes. And if your goal is to minimize m, which is q times t, if your goal is to come up with a code with relative distance 1 minus epsilon, such that q times t is minimized, and I want you to have n code words, the best I'm aware of is in some regime you do this, in some regime you do that. Okay? And it's an open problem whether there's anything better. There's a lower bound. We'll see it later in the class, actually. There's a lower bound by alone, which says that any incoherent matrix, forget about codes, just any incoherent matrix must have m, which is at least 1 over epsilon squared times log n over log 1 over epsilon. Okay, so if epsilon's a constant, then that actually is fine. That matches that. If epsilon's really small, then again that matches that, but we don't know how to match it in between. Okay, so good. So that's point query. You could ask about heavy hitters. I think I mentioned this last lecture. I'll just say it again in words. So one thing you can do, this is for any epsilon incoherent pi. Okay, so one thing you can do to solve heavy hitters is there's a black box reduction, right, from heavy hitters to point query, which works as follows. Instantiate a point query data structure with error epsilon over 4. Right. That means anyone who's actually a heavy hitter, if you point query him, you'll see at least 3 epsilon over 4. Anyone who's not even an epsilon over 2 heavy hitter, right, you'll see something less than epsilon over 2 plus epsilon over 4. You'll see something less than 3 epsilon over 4. So the algorithm is do your point query sketch, and then now at the end, loop over every single index from 1 to n, and report the ones that have a mass at least 3 epsilon over 4. That's your list. Okay? So that works. It's really slow, because n we're imagining as being huge. We'll see how to fix that soon. Okay. So good. Notice that we use the probabilistic method to show that this code exists. But if someone one day came along with like an explicit construction of this code, the algorithm would be totally deterministic. There's no randomness in this algorithm, right? And if you use Reed-Solomon codes, there's no randomness at all, right? Okay, so this is a deterministic approach, which has certain advantages, which I'll say in a second. But there's also a randomized approach, which has certain other advantages, namely that it's more space efficient. Okay, so randomized point query. So the first thing I'm going to show you is the what's called a CountMin CM sketch. This was introduced by Cormode and Muthukrishnan in 2005. Well, it was the journal version anyway. And I'm not making any accusations, but just notice. Actually, they have a FAQ where I think they ask about the naming of the sketch, and they sort of evade. I mean, they created the FAQ, I guess, as a joke for this question. They avoided answering whether there's any correlation here. So how does this work? So it's based on hashing. Okay, so the way the algorithm works is I'm going to have this grid of counters. And for each row of this grid, I'm going to have a hash function. So there's h1, which maps 1 to n into 1 to t, up to hl, which maps 1 to n into 1 to t. Okay? And when an index I comes along, someone updates xi. They say, I want to add v to x sub I. What I do is I go to the first row and I hash I, and that tells me some random entry. And I go to the next row and I hash I, and I hash I, and I hash I. And I add v to each one of these. Okay, so there are counters C, A, B, for, so I guess if A is a row, for A between 1 and L, and for B between 1 and T, let's call it CAB is going to store for us the sum over all I from 1 to n such that HB or HA of I is equal to B of xi. Right? So this is CAB is the ath row and the bth column. It's going to store everyone who hashed by the ath hash function into B. Right? Or if you like thinking about pies, you have your sketch matrix pi. M is going to equal basically T times L. And pi looks something like this. If you look at a column, this is column I. Imagine the rows are sort of segmented into, there are, I guess, L chunks of rows, right? And each chunk of rows has a 1 in it in a random location. And where's that 1? That 1 is dictated by the hash function. So this is H1. H1 tells you where that 1 is. H2 tells you where that 1 is. Each one of these has width T. Yeah. So we're not, yeah, so I mean, you're saying this looks quite similar to the matrix that was constructed, the epsilon incoherent matrix constructed using codes. So the thing that's going to happen here, though, is we're not going to have the guarantee that any two columns, like for all pairs of columns I and J, they don't intersect much. We'll just have the guarantee that, that our error random variable will be small with good probability. Yeah. Right. So you'll have that. So if you fix a pair, if you fix two different I and J, like columns of this matrix, and you ask, what's the, you want to say with good probability they don't collide much. That will happen from pairwise independent hashing. But with the codes, we wanted something even more. We wanted that for all pairs, they didn't collide much simultaneously. So what we did was we did a union bound. So to do a union bound, your failure probability has to be something like 1 over n squared. And if you try to get that out of just pairwise independence, you're going to be screwed, basically. Yeah. Or no, it'll be like a constant. Basically, if you want failure probability delta, pairwise independence is going to force you to set T to depend on 1 over delta. Whereas we really want things to depend on log 1 over delta. Yeah, it's like the same issue we had in the first lecture or the second one where we did the median of estimators. We could have just done the average of many estimators, but that would have made us have a 1 over delta dependence. So we did the median of a bunch, right? So it's the same kind of issue. That's right. Yeah, you could use pairwise independent hash functions and blow up T by a lot. Yeah. Your final sketch will have even more than n squared rows. That's right. Good. And actually, in fact, these H's will be from a 2-wise family. We will use pairwise independent hashing. And the H's will be independent of each other. Okay, good. So now, We just need to show that good things happen. Okay. So for point query, let's say for epsilon point query, with now this is a randomized algorithm, Monte Carlo. It has some failure probability. So with failure probability delta, meaning we're going to output xi plus or minus epsilon times the L1 norm with probability at least 1 minus delta. We're going to set t to be something like 2 over epsilon, and L to be something like log base 2 of 1 over delta. I don't know why I put seals all of a sudden when I haven't been doing it before. Let's just pretend, it has to be an integer, but put a ceiling if you so choose. Okay. Good. So claim, I should tell you what is the estimate for the point query. We're going to output, this is why it's called the CountMin sketch, because we store a bunch of counters, and then our estimator is going to be the minimum. So output the min over all I from 1 to L of C of, not I, let me say R. Okay. Okay. And I should say, here I'm assuming, I'll say something, removing the assumption in a second. I'm assuming what's called the strict turnstile model. So I'm assuming there's someone gave us a promise that said all entries in X are non-negative. So for example, if xi is the number of packets addressed to IP address I in a network traffic stream, then xi is a count, so it better not be negative. Okay. Though there are situations where you care about negative counts. So for example, suppose I have a count vector from today and a count vector from yesterday. And I want to know what are the things that differed a lot between today and yesterday. What would I do? I would do this sketch to both of those vectors separately, and then I would subtract the sketches from each other. And since the sketch is linear, that subtraction will be the sketch of the difference vector. And then I will ask what's heavy in the difference vector. And that can have negative entries, right? So there are cases where you care about turnstile versus strict turnstile. Now, in the first case I said, not only do you know that all the xi's are non-negative, but you know that there are never any deletions ever. So that's the insertion-only model. And on pset 2, which will come out later today, you'll see that there's an even more efficient, even deterministic streaming algorithm for insertion-only heavy hitters. Okay, but anyway, so let's assume the strict turnstile model for now. Our estimator is going to be, so you want to estimate xi, look at all the places he hashed to, the L different places, and output the minimum of those. Why the minimum? In the strict, so what is in this bucket, in this counter? Xi is in here, plus some other stuff that collided with him. But if it's in the strict turnstile model, all the stuff that collided with him is non-negative. So that can only make it bigger. So really what you want is the count, all of these are overestimates of xi. So what's the best overestimate? It's the smallest of all of them. That's why you're taking the min. If you didn't have strict turnstile model, if you had turnstile, what do you think you would do instead? Yeah, you would take the median. And a similar analysis, you'll see in a second, is going to give the same kind of performance. The constant factors will differ. Okay, so the claim is that query of I is xi plus or minus epsilon times the L1 norm with probability at least 1 minus delta. Okay, and why is that? Okay, so fix I. Let Zj, let's call it Zrj, be the indicator function of the event. Actually, fix I, and also fix R from 1 to L. Look at a particular R. And now let Zj be equal to, it's an indicator function of them colliding under the hash function, under the rth hash function. 1, if h of r of j is equal to h of r of I, and 0 otherwise. And now, notice that C r hr of I is equal to, well, xi is definitely in there, plus the sum of j not equal to I of xj times Zj. Right? So this is the error. Okay. Now notice that the expectation of the error is sum over j not equal to I, xj times the expectation of zj. But what's the expectation of zj? Yeah, it's 1 over t because of pairwise independence, right? If you look at two guys at a time, namely I and j, the probability that they collided under this hash function is 1 over t by pairwise independence. So this is equal to sum of j not equal to I, xj over t, and by our choice of t, that's less than or equal to epsilon over 2 times the L1 norm. Right? So the expectation is at most this. And again, because of the strict turnstile assumption, E is non-negative. So that's not going to, well, it's not that serious. But the probability that E is bigger than epsilon times the L1 norm is less than a half by Markov, right? Now, if it hadn't been strict turnstile, what I would look at really is like the expectation of, I would say that this error is at most the absolute value here, right? And then I would bound that, and that would still be some non-negative random variable. Okay. So right now, basically everything I did here. So let me say I could say this error is at most that, right? And then the expectation of the error is I could have done that, and I would have still gotten something like that, even in turnstile. So then the probability that the error is bigger than epsilon times the L1 norm is at most a half. Okay. Now is where I'm going to use the strict turnstile assumption. When does the min estimator fail? When does it fail to give me that kind of guarantee? Right. So I know that in strict turnstile, all my estimates are overestimates. So certainly, none of them will give me something less than xi. So when will the min fail to give me something less than xi plus epsilon L1 norm? Yeah. Yeah. Every single one of the counters has to fail for the min to fail, right? If they're all giving me overestimates, they all have to fail for this to fail. And they're independent of each other. So the probability that they all fail, so the probability that the min estimate, which was the min over R of CR HRI. Probably the min is bigger than xi plus epsilon times the L1 norm, is at most 1 over 2 to the t, which by our choice of t is delta. Right. Now, if you had been working with turnstile, where some of these, yeah? Oh, yeah, thanks. No. If we had been working with turnstile instead, you know, some of these things could be overestimates, some of these things could be underestimates, right? So what we would do is take the median instead. And what we would say is the probability that the error is bigger than, you know, 3 epsilon times the L1 norm is at most, you know, a sixth or something. And then by Chernoff, the median, you know, when would the median fail? Half the people have to fail. But only a sixth fail in expectation. So the probability that we're bigger than our expectation by a factor of 3 is exponentially small in L by Chernoff, which again is delta. So you could do that median Chernoff approach, and it would work. It would just get you a worse constant factor, basically, because you lose a constant factor in the exponent from Chernoff. And also, it's not enough to just make this thing a half. You need to make it something a little bit less than a half. Right. So questions? Notice, by the way, that what is this giving us at the end of the day? This is giving us m, which is O of 1 over epsilon times log of 1 over delta. Right, so over there, both of those solutions got 1 over epsilon squared. Here we're getting 1 over epsilon. So if delta is not super small, you know, this is better. That's not an accident. I'm not going to cover it in class, but there is a lower bound that's been shown that says that any deterministic scheme for point query, you really do need 1 over epsilon squared. Okay. So you do lose something by requiring your algorithm to be deterministic. Okay. Now, what do you gain? You know, one thing that you lose by using a randomized algorithm like this one is if you're doing, like, say, you're doing data mining, you're doing some data exploration, right? And you're running some randomized algorithm on your data that has some probabilistic guarantee. Like the probability of success is 99% or something like that. You'd like to say that, okay, let's say your failure probability is delta. You'd like to say if my failure probability is delta, I can make 1 over delta queries on my data. And by union bound, there's some, you know, chance that all of my queries succeed. Okay. Now, if you're doing data mining, you know, when is there a problem with that argument? It's a little subtle, maybe. Yeah, exactly. If the queries are adaptive, then there's a problem, right? So if the next query you make, if you choose to make a query based on what the answers to the previous queries were, then the query you're making is correlated with the internal randomness of the data structure. And then the failure probability guarantees like just don't apply anymore. All bets are off. Okay? Right? The guarantee here is if you have a query in mind and you don't know the internal randomness of my data structure, then once I see your query, I'll be correct on it with probability 1 minus delta. But as I answer queries, the answers I give might reveal, you know, they're correlated with the randomness I'm using. So if you start asking me questions based on what you're hearing from me, right, then I'm not really a randomized algorithm anymore that's providing good guarantees. So as an extreme example, if the way I answer queries for you, I give you my answer and then I append my internal random string, so you just know all of my randomness, then you can go and cook up a query that just completely screws me over, right? So these kind of randomized guarantees are not applicable when you're doing adaptive data analysis. So if you're doing something adaptive, then it's better to, one thing you can do is use a deterministic algorithm because it just always works regardless of how you choose your queries. Yeah. Yeah. So you say if I'm not trying to screw the system, but I guess it depends on how you formalize that. So, one thing that would work is if I determined all the queries I ever want to make ahead of time, and then once your algorithm is prepared, I just ask all those queries I had prepared ahead of time to you, and then you answer them. That's perfectly fine. The problem is as soon as you have adaptivity. So, maybe I'm not trying to screw your system, but yeah, I mean, the theorems just don't apply, right, to this situation when I'm asking queries based on your answers. And that's a general thing to watch out for with Monte Carlo randomized algorithms. By Monte Carlo, I mean there's a failure probability, as opposed to Las Vegas, where they're always correct, but the running time is random. Okay. You said, so I have a set of possible queries I might want to ask, and then I narrow it down to a subset based on how you actually answer things. I mean, yeah, I guess it really depends on exactly the setup because, you could imagine, what if the initial set of queries I might ask is like the set of all queries? And then I narrowed it down to a subset, right? So in that case, you really can't say anything. But yeah, I don't know a good answer, an answer that is more meaningful than that. Yeah. Actually, there is some, so for people in the audience who, I mean, this is only sort of related to what I'm saying. Well, it's not really a streaming thing. It's just the general thing about adaptive data analysis. There's been some really nice work by people who were doing differential privacy exactly on this problem. So showing that you can use differentially private mechanisms to do adaptive data analysis well and not harm the privacy of people in the database. But it's a different topic. But anyway. Yeah, and actually there was a paper by Moritz Hart and David Woodruff on adaptive queries in kind of in this context, where they show that you can really be screwed by adaptive queries in certain contexts. Okay, so that was point query. Now, if you want to solve the heavy hitters problem, which I just erased, you want all the people who have at least an epsilon fraction of the L1 weight. Again, you would actually use, you would do point query with epsilon over 4. What would you set delta to be? Remember the algorithm. I'm going to loop over every index I from 1 to n, and I'm going to do a point query. And I'm going to return the list of all people that answered at least 3 epsilon over 4 times the L1 norm. Let's assume strict turn style. Log of, so log of 1 over n? Log of 1 over n is a negative number. Yeah. Okay. So do point query. So epsilon heavy hitters, do point query with epsilon over 4 error and delta at most what? Let's say delta less than So suppose that I want my heavy hitters algorithm. Actually, now it's, let's say I want the alpha heavy hitters. I want the alpha heavy hitters with probability 1 minus eta. Okay, just so that I'm not using the same variables in both algorithms. So I'm going to do point query with epsilon equal to alpha over 4. And delta is going to be what? Delta to the n. So okay, so delta to the n less than eta. So here's what I'll do. I'll set delta to be eta over n. Right? Because at the end of the day, how many point queries am I doing? I'm doing n point queries. I'm point querying every index I from 1 to n. What I'd like to say is that with probability 1 minus eta, all of them succeeded. So I'm going to do a union bound. Right? This is not adaptive. I've decided my queries ahead of time. I'm querying all n things. So the probability that any of them fail is the sum I from 1 to n of eta over n, which is eta. So by a union bound, this works. So this implies the space of the heavy hitters sketch will be 1 over alpha times log of n over eta. And also, the query time will be O of basically n times log of n over eta. So that's a pretty bad query time. So faster query, and I'll describe it again in strict turnstile because this time it actually is simpler to do it in strict turnstile. It's not just the difference between min and median. And this approach, again, this approach is in the CountMin sketch paper itself. So the answer is use a tree. What do I mean by that? So we have these n indices from 1 to n. We don't know which ones are heavy hitters, right? So let's write these n indices as leaves of a tree, and let's make a perfect binary tree on them. Okay? So there are log n levels here. Okay, and what we're going to do is we're going to have a CountMin sketch CM0. We're going to have a CountMin sketch CM1, all the way down to a CountMin sketch CM log n. Okay. So notice that it's nice to think about it in terms of reductions. This is not really specific to CountMin sketches. Okay. So that first part over there is a reduction that says if you can solve point query with epsilon equals alpha over 4 and delta equals eta over n, it implies a heavy hitters algorithm. Now you can go off and implement that point query algorithm however you like. Again, what I'm going to show you is if you have, well, right here, if you have a point query data structure, you can use it in this tree fashion. You can use log n of them in parallel in this kind of tree structure to solve heavy hitters. We'll also use in this solution, we'll also crucially use the fact that the CountMin sketch always provides an overestimate. Okay, we will use that. So that so if you have those two things, if you don't ever underestimate, okay, if you don't ever underestimate and you have strict turnstile. Okay. If you don't underestimate, you have strict turnstile. Actually, you don't need the underestimate thing. Okay. If you have strict turnstile and you have point query, then you can do this tree thing. So let's see what I'm going to do here. Okay. I will use strict term style. So the thing to have in mind here is that we're actually sketching not just one vector, but we're sketching log n different vectors in parallel. Yeah. Yeah. With the CountMin sketch. Yeah. Maybe you have, but maybe there's some other crazy algorithm that that does underestimate. But if you have strict turnstile, you can use a point query data structure in this tree way. So there are log n plus 1 different vectors that are being sketched. At the bottom, there's just the vector x. It's n-dimensional. One level above, there's another vector, okay, which is n over 2-dimensional. Each node is a coordinate. And what is the weight of this node? It's the sum of its children. Okay? And it's the same for all of them. In general, whenever you look at any level, the weight on a node is the sum of the weights of its two children, which inductively implies that the weight of this node is basically the sum of the weights of all of these, of everyone under it, of all the leaves under it. The way I'm going to use strict turnstile is to say that since all of these are non-negative, there are no cancellations, right? Which means that if a node has a heavy hitter in its subtree, then that node will also be a heavy hitter at its level. Because the L1 norms the L1 norm doesn't change from level to level, again, because there are no cancellations. Okay? So L1 is the same at every level. Okay, and also, node U contains heavy hitter amongst leaves in its subtree. Implies that U is a heavy hitter at its level. Okay? So now what am I going to do? Here's the algorithm. So first of all, the update algorithm, I have log n, 1 plus log n different count sketches. The update algorithm is whenever I update some node, I look at it, I look at the leaf there, and I look at its root to leaf path, and I update every single one of these nodes by that amount. Okay? So I update log n different CountMin sketches, or log n different point query data structures. That's how you do an update. How do you do a query? Remember, updates were already fast from that first thing, right? The thing that was slow was the query. Now, how do you do a query? The way you do a query is you start at the root. Okay, the root, and what you're going to have is, at any point in time, you're going to have like 1 over epsilon different fingers at different places. Okay? So you start off with a finger on the root. And whenever your finger's on something, it's because it's a heavy hitter. Is the root a heavy hitter? Yes. It's a 1 fraction of all the L1 mass, right? The weight of the root is the entire vector. And now you ask yourself, okay, which of the children of this node are also heavy hitters? So I'll query this child, and I'll query this child. Now, because of the second bullet over there, if there's a heavy hitter in this tree at all, this will be heavy, and same thing here. If it's not heavy, I won't recurse down there. And then it's like a DFS, basically, or a BFS. I'm imagining a BFS. And then now I look at these two children, and then maybe they're both heavy. So now I look at these two children. I look at these two children here, these two children. Maybe all 4 are heavy. right? And then I'll just follow down the tree until I get to the heavy people. Okay. Now, in reality, no question. Forget about failure probabilities. Okay. How many, right? So this here, this is a one-dimensional vector. This is a two-dimensional vector. In general, at level j, it's a 2 to the j dimensional vector. In that vector, how many entries could actually be epsilon heavy hitters? At a single level, how many of these nodes can actually be epsilon heavy hitters? At most the size of the level? What's? Oh, right. Well, I mean, no, well, I don't agree with that. The reason is, like this guy might not have any heavy hitters under him, but there might just be a bunch of noise that adds up and makes it look heavy. So at any given level, you might have some people who we think they're heavy when they're actually not heavy. Okay? But how many heavy hitters are there at this level? It's something we've already answered before. Right? How many epsilon heavy hitters can there be in a vector? 1 over epsilon, right? This is a vector. Granted, it's some 2 to the j dimensional vector, but whatever, it's some vector. Only 1 over epsilon entries in that vector can be heavy hitters in that vector, right? So what that means is, as we're doing this DFS, our finger will only ever touch, assuming that all these CountMin sketches are, assuming that every query we ever do is answered correctly, we'll only ever DFS down to vertices that are actually heavy hitters at their level. So we're only ever going to touch 1 over epsilon, or 2 over epsilon, maybe, vertices on every level. So the number of vertices we touch is at most 2 over epsilon times log n. They're log n levels. Right? So there are only, at most, 2 over epsilon nodes at any given level which are epsilon over 2 heavy hitters at that level. Which implies that if all point queries are correct, I guess I said I'm using alpha. If all queries are correct, if all point queries are correct, we only touch at most 2 over epsilon times log n vertices during this DFS. Right? So we don't have to actually try all n vertices like the first solution. We can just do this tree thing. Question for you. So we're instantiating these point query data structures at every level. There are log n of them. For each one of these CM data structures, we have to set its epsilon and its delta. Right? For each CMJ data structure, what should we set epsilon to be? Right? What do we need to detect? For a node, we need to make sure that it's an epsilon heavy hitter at that level. And we don't want to touch people who are not even epsilon over 2 heavy hitters, or alpha. Sorry. If it's an alpha heavy hitter, we want to touch it. If it's not even an alpha over 2 heavy hitter, we don't want to touch it. So what should we set epsilon to be in the point query data structure? Alpha over 4, just like before. How about delta, the failure probability? Right? We want a union bound, and we want to say that every query we ever make succeeds. right? So what we should set delta to be is eta, the final failure probability that we want, which is eta, over the number of queries that we make. Okay? Now, how many queries? So we have our fingers on a certain number of heavy hitters at this level. There are only 2 over epsilon of them, right? And for each one of these things that we know that is a heavy hitter on this level, we're going to query its 2 children. So there are 2 over epsilon people, or 2 alpha, there are 2 over alpha people at this level that we have fingers on. So the number of children they have total is 4 over alpha, right? So the total number of queries we make is something like 4 over alpha times log n, basically. Right? So that implies that the space of any particular one of these heavy hitters is going to be O of 1 over alpha times log n over alpha eta. But we have log n different CountMin sketches, or log n different point query data structures. So that implies that the total space is O of 1 over alpha times log n, times log n times log of log n over alpha eta. Okay? So this is the final thingy. And again, our query time for heavy hitters will be something like 1 over alpha times log n times some other smaller stuff. So we improved the query time from n, roughly, to 1 over alpha times log n, roughly. Which is, I mean, it's not going to be better than 1 over alpha, because the output size has 1 over alpha things in it, right? Potentially. Okay, great. So, questions? Yeah. Right, so what is the time to update a CountMin sketch? It's log 1 over delta, right? Because there are these log 1 over, basically L is going to be log 1 over delta. So the time to update a single one is log 1 over delta, which is something like basically log n plus log 1 over eta plus log 1 over alpha. So your final update time will be that times log n, right? So it's still, the update time is worse because it's, but it's still polylog anyway. Oh, sorry, say it one more time. Yeah, so that's exactly this, right? So this is storing all of them. So storing just one of the CountMin sketches takes you this, machine words. Storing all of them is an extra log n, because there are log n of them. Yeah, that's right. I mean, you could ask, top secret, even though I'm being recorded, you could ask, can I maintain that same kind of space and an update time and get that kind of query time, right? Like the best of all worlds. So, I mean, that's something that with some, friends we're currently looking at. We think we have something, but, work in progress. And unfortunately, it's not looking as simple as what I just presented on the board. So. Okay, great. So that's one thing. So another problem, I'll say one thing about another kind of guarantee. So we saw point query, we saw heavy hitters, right? So heavy hitters, as I mentioned, is kind of an L infinity L1 guarantee. something that we'll see soon, later in the course, but soon, is something called compressed sensing, which is all about various kinds of guarantees you can get. And one such guarantee is, can we get L1, L1? What does that mean? What do I mean there? What I want is, I want to return an x tilde such that x tilde L1 norm is at most 1 plus epsilon times what I'll call this. Okay, so what is x tail? X tail k is take x and just zero out. Imagine that x is actually a k-sparse vector plus noise. So x tail is the noise. X tail k is the noise. So just zero out all the top k entries in magnitude and keep the noise. So in particular, if x is actually k-sparse, then this is 0. Okay? So the question is, can I get an x tilde that does almost as well as the best k-sparse vector approximation to x in this kind of L1, L1 sense? Okay? And kind of point query can give this, or let me not say point query, but specifically the CountMin sketch can give this. Okay, and we'll see why. Can give this with the support size of x tilde even being, at most k. So the CountMin sketch can actually give you a k-sparse vector that does almost as well as the best k-sparse vector approximation to x under this kind of L1, L1 guarantee. In particular, if x is actually k-sparse, then this right-hand side is 0, which means that you'll actually recover x exactly. Okay. So how do we do that? So first of all, what I want to say is claim so let's say if the CountMin sketch has t being at least, let's say, k over epsilon, and so even not just k over epsilon, but let's say L being theta log 1 over delta, then with probability 1 minus delta, we'll have that xi tilde is equal to xi plus or minus an error term, which looks like epsilon over k times x tail k. Okay? So normally, what did we say? We said that if you're using the CountMin sketch to do point query, then if you have a t by L CountMin sketch grid, your error will be xi plus something like, let's say, some constant times k over epsilon. Your error will be something like 1 over t times the L1 norm. That's why we set t to be like 1 over epsilon, right? But I claim that not only do you get 1 over t times the L1 norm, you actually get 1 over t times the L1 norm of the t tail. Okay? So I'm not going to write down the proof formally, but basically it goes like this. Before we just said, look, the expected L1 mass of the people who collide with you is a 1 over t fraction of the L1 mass. So then we did a Markov and Chernoff bound, or Markov and Mien kind of thing. Another thing you can say is if you're hashing into t buckets, let's say you're hashing into 10 t buckets, right? Then with pretty good probability, like with 9/10 probability or some high, good constant probability, none of the top T guys will collide with you, right? If you're hashing into 10 T buckets, then the expected number of top T guys who collide with you is like a 10th. So the probability that it's at least 1 is at most 1/10. So with good probability, none of the top T guys will collide with you. And then if you condition on that event, okay, so let that be one event. And the other event is, look at the tail. What fraction of the tail collides with you? An epsilon fraction of the tail collides with you, right? So if those two events happen simultaneously, A, the top T guys don't collide with you. B, only an epsilon fraction of the tail collides with you, right? Then you're getting this kind of error. So really, CountMin actually gives you a better error than what I said before. You can get an error in terms of the L1 of the tail and not just the L1 of the entire vector. Okay. So let's just take this as truth. Good. So in fact, this is even tail of k over epsilon. Okay, so it's tail of T basically. So now good. So how are we going to do a sparse approximation? Given x tilde from the CountMin sketch output, where x tilde I is equal to the query of I, we're going to set kind of y as being, okay, so let T subset of n correspond to the largest k entries of x tilde in magnitude. Okay? What we're going to do is we're going to set y to be x tilde t, meaning x tilde projected to the coordinates in T. Just keep, it means basically keep the head. Okay? So everyone, keep the top k coordinates and zero out everyone else. And that's going to be our approximation. And the claim is that if you look at x minus y L1 norm, that's going to be at most 1 plus epsilon times the tail. And I think we don't have much time. So let me say this. Actually, I think, yeah, this is not too bad to prove. Let's just prove this. Okay, so proof. Let S denote the head of X, and also, as we said, T is the head of X tilde. So these things are subsets of 1 to n, right? These are the heaviest, the locations of the heaviest entries. So x minus y L1 norm is equal to, well, y only has mass in T, right? So this is equal to x minus x of n minus T plus xt minus yt, right? This is just the L1 mass in X outside T, and then this is what's left over. Y only has mass in T. And for this part here, what I'm going to do is I'm going to, oh, sorry, not this is T here. Okay. And now what I'm going to do is I'm going to subtract yt and add it back this is at most x1, well, this is equal to x1 plus xt minus yt plus yt plus the same thing again. Okay, and then we use triangle inequality. This is at least x1 minus yt plus 2 times xt minus yt. Okay. At most, sorry. And then I'm going to say, look, yt gives you the biggest mass. T is the biggest locations of y, right? So definitely, it's even smaller if you put s there. Okay. Right? T is the location of the largest entries of y. S is the location of the largest entries of x. And now what I'm going to do is I'm going to do the same trick. I'm going to subtract xs and add it back. So I'm subtracting xs and adding it back. This is at most x minus xs plus xs minus ys plus 2 times xt minus yt. But this is exactly, this is all L1 norm. This is exactly the L1 norm of the tail. And now we're going to use the fact that CountMin gives us this pointwise guarantee. For each entry in S, the difference between xi and yi is at most that, epsilon over k times the L1 norm of the tail. And similarly here, for each entry in T, it's at most that, right? How many entries are there in S? K. How many entries are there in T? K. Those k's cancel this k, and you get basically epsilon times the tail from this and another 2 epsilon times the tail from that. So this is at most 3 epsilon times the norm of the tail. So really I could have said, the claim really I could have put, let's say, 3 epsilon. Okay? So you can kind of get this L1 sparse approximation guarantee out of CountMin as well. Okay, so that's really all I want to say about CountMin and this incoherent stuff. At the beginning of next lecture, I'll say one more thing about heavy hitters, and then I'll move on to move out of heavy hitters. Okay, and we'll look at some other stuff. And you'll have some piece-up problems, a couple of piece-up problems that deal with heavy hitters.